Okay, good morning. So uh, before Thanksgiving, we were talking about the problem of adding angular momenta. So, so the idea is we have two angular momentum operators, J1 and J2, and we want to express the orthobasis for these in two different ways. So this is going to be some review. So there's one complete set of commuting observables that we can write down, which is J1 squared, J2 squared, J1z, and J2z. Those all commute with each other. And because they're a complete set of commuting observables, we can write down a basis, which is called the product basis. Okay, and we can label this in different ways. One way is we write J1, J2, M1, and then I'm gonna put a colon for M1 and M2. Or sometimes I can just omit the J1 and J2 and just write it as M1 and M2. Okay, so these we omit if they're understood. For example, if we're doing a lot of things with the same J1 and J2, we don't want to write them every time. And then the colon is optional if you need it to distinguish from the other basis that we're about to write. And so the other complete set of commuting observables is J1 squared, J2 squared, and the total z component, Jz, and the total j squared. I guess it's traditional to write them in the opposite order. So I could write j squared and j sub z. Okay, and this is the total angular momentum basis. Okay, and so we can label those states as J1, J2, J, and just M. And so we would never put a colon there. That's how we can tell apart the product basis from the total angular momentum basis. All right, so then we did the example where J1 and J2 were both spin 1/2. So if we add together two spin 1/2 operators, we can write the result as 1/2 tensor product 1/2 gives a total of either 1 or 0. So that's how we write this. The left-hand side corresponds to the product basis. This is J1, this is J2. And these two things are both J. Okay, and so then we constructed in the total spin basis what the states are and had a recipe for turning them into the product basis. Okay, and so we can write this as the total spin basis states as 1, 1, and 1, minus 1, and 1, 0. And together those form a triplet because they all have total spin 1. And these are equal to up arrow, and down arrow, and 1 over root 2, up arrow, down arrow, minus down arrow, up arrow. Okay, so there's a equality between the two bases that looks like that. And then there's the singlet state, which is total spin 0 and its z component, therefore has to be 0. And that's 1 over root 2. This should have been a plus sign. And this is up arrow, down arrow, minus down arrow, up arrow. Okay, so then we emphasize the fact that depending on what you're doing, you would want to use one basis or the other. And a good sign that you might want to be working in the product basis is the fact that if you have a dot product of the two angular momenta, you can write this as 1/2 s squared minus s1 squared minus s2 squared. And that's going to be diagonal in the product basis. It's not diagonal in the, it's not diagonal in the product basis. It's Monday. It's diagonal in the total basis, not in the product basis. Okay, and more generally, if I have any two angular momenta and I take their dot product, a lot of times angular momenta are associated with magnetic moments, and then the Hamiltonian for two magnetic moments is proportional to their dot product. So this comes up quite a bit. This is 1/2 total angular momentum squared minus the individual angular momenta squared. So again, this is diagonal in the total basis and not in the product basis. And so for general J1 and J2, one writes J1 tensor product J2 is equal to J1 plus J2, or J1 plus J2 minus 1, or every other combination until you get down to the absolute value of J1 minus J2. Okay, and those things in parentheses, each one of them is labeling the total J for that set of states. Okay, so what we're going to work out today is the example of orbital plus spin. Okay, and so the thing that will go along with that is L dot S is equal to 1/2 J squared minus L squared minus S squared, which is equal to H bar squared, I'm pulling out that common factor, over 2 times J plus 1 minus L times L plus 1 minus S times S plus 1, but S is 1/2 always, so this is 3/4. Okay, and the allowed values of J are L plus 1/2 and L minus 1/2. Those are the only allowed values. And so what we can write is, if you take the tensor product of an orbital angular momentum and a spin, the orbital angular momentum has to be an integer. The spin is always 1/2 for a spin 1/2 particle. And so this is equal to L plus 1/2 and L minus 1/2. Those are the total angular momentum basis labels. Except you have to be careful, because if L is equal to 0, then L minus 1/2 can't exist. You can't have the total angular momentum quantum number be less than 0. So this is only true if L is greater than or equal to 1. And if L is equal to 0, then all you get is the 1/2. Okay, so those are the two possibilities. All right, so the total basis states, total angular momentum basis states, are labeled by L plus 1/2 and their M value, and L minus 1/2 and their M values. These are eigenstates of L dot S. That's what they're mostly good for. And in fact, let's work out their eigenvalues. Okay, so what we do there is we take this formula up here and we plug in the different possibilities for J. Okay, and so the first possibility is H bar squared over 2 times L plus 1/2 times L plus 3/2 for J, minus L times L plus 1 minus 3/4, but we don't want to leave it like that because that's not simplified. And so when you multiply all that stuff out, you get just h bar squared times L over 2. Okay, so this has a very simple eigenvalue for L dot S. And the other one, the other combination is h bar squared over 2, L minus 1/2, L plus 1/2. The rest of it's the same. Okay, and then when you simplify that, it's minus h bar squared L plus 1 over 2. These ones have degeneracy. Let's count the degeneracy. So it's 2 times j, which is L plus 1/2, plus 1. That's the different number of m values, which works out to be 2L plus 2. And these ones have degeneracy 2 times L minus 1/2 plus 1, which is 2L. Okay, and so the total number of states is equal to 4L plus 2 in this case. All right, so we're going to go ahead now and construct the total angular momentum basis states in terms of the product states. Okay, so again, the product basis, we can start by writing them in the most general form, which would look like this, with a colon. But then we observe that, oh, we don't need to write down L and S because we know what they are. They're going to be fixed in everything we do today. So we just write it as MLMS. Okay, but we could also write this, and so we'll do it without the colon, as just ML up arrow and ML down arrow. That way I know if I'm using up arrow and down arrow that I'm talking about the product basis. And then I don't need to write the colon here to remind me that I'm talking about the product basis. Okay, and then there's the total basis that we want to construct out of these things, which is again L and S, and J and M are the labels. So we can just write this as J and M. Okay, so we want to construct these from the product basis. All right, so let's start with the case where L is equal to 0, because that's going to turn out to be super easy. And the reason it's super easy is because it turns out the bases are the same, actually, in this special case. So to see that, let's take a product basis ket, for example, L equals 0 up arrow. Okay, if L equals 0 and you have spin 1/2, then the only thing the total angular momentum can be is 1/2. And if the spin is pointing up, the only way that the total angular momentum along the z direction can be pointing is up, and that's the plus 1/2 direction. Okay, so this is in the product. This is in the total. Okay, and then the only other state that exists is 0 down arrow, which has total angular momentum 1/2 and projection along the z direction minus 1/2. So again, this is the product and the total. And so anything that's a basis element of one is a basis element of another. These are already eigenstates of j squared and j sub z. Okay, so that was too easy. Now let's do the case where L is not 0. Okay, and so what we're going to do here is we're just going to start with a strategically chosen element of the product basis. Namely, we're going to start with the state which has ML, MS equal to the largest things that it can possibly be, which for M sub L is equal to L, and for M sub S is going to be up arrow. All right, so let's examine that state, and we're going to take JZ acting on it. And to do that, we're going to write J sub Z as L sub Z plus S sub Z. So we do that. Okay, and then L sub Z acting on this state just gives H bar times L, because L really here is standing for M sub L. And S sub Z acting on up arrow is going to give H bar times 1/2. So the whole thing is just H bar times L plus 1/2 acting on the original state back, which proves that it's an eigenstate. Okay, so again, just like the L equals 0 case, this is an eigenstate of J sub Z with, we've just shown, eigenvalue H bar times L plus 1/2. And so if that's true, it must also have J squared eigenvalue, H bar squared J times J plus 1, where J is equal to L plus 1/2. Okay, so we've shown that this thing is already an orthobasis of the total angular momentum basis. And therefore we know that L plus 1/2 is equal to L up arrow. This is J, this is M sub J, or just M. This is M sub L, and this is M sub, telling you what M sub S is. Okay, so we're done with one state out of all the 4L plus 2 states. And now we're going to use this to construct all the others. So in particular, we're going to start with all other states of the form L plus 1/2 and M. Okay, and so the strategy is to apply the operator J minus many times. So we're going to apply J minus many times. Each time we do it, it will lower the value of M by 1 unit. Okay, so the key formula that we're going to need, that we're going to apply over and over again, is this, that J minus acting on an angular momentum eigenstate is equal to H bar square root of J plus M times J minus M plus 1 times the same state with M lowered by 1 as promised. And this is equation 7.1.22 in the notes. And that's where we derived it. And this is written for J, but we're going to use this also with J replaced by L and with J replaced by S, because its derivation only relied on the fact that it was an angular momentum operator. And so it's true for any angular momentum operator, anything that satisfies the same commutation relations, including J, L, and S as well. Okay, so the first thing we're going to do is apply this with J equals L plus 1/2 and M equals L plus 1/2. And that's because we already know what that state is, so it's a good thing to apply it to that. Okay, and so what does that tell us? It tells us that J minus L plus 1/2, L plus 1/2 is equal to H bar square root of 2L plus 1 times L plus 1/2, L minus 1/2. I have to remember to lower M by 1 unit. Okay, and so now the thing is that this is the thing we want to find, and this is the thing we know. So we're going to rewrite this equation as L plus 1/2, L minus 1/2 is equal to 1 over H bar square root of 2L plus 1. And we're going to rewrite J minus as L minus plus S minus. And we're going to rewrite the state that we know here in terms of the result we got for it, which was L up arrow. Okay, so this is L up arrow. This is written in the product basis, and the left side is written in the total angular momentum basis. Okay, now we're going to use the same formula here with J is L and J is S. And so we write that as follows, that L minus acting on L up arrow is equal to H bar square root of L plus L times L minus L plus 1 times L minus 1 down up arrow. Okay, so the L minus operator just ignores the up arrow label, and it only acts on the L label, the M sub L label. Okay, and then we should simplify that a little bit and write that as H bar square root of 2L times L minus 1 up arrow. All right, now we do the same thing with S minus. This time it ignores the first label and just acts on the spin label. So now we get 1/2 plus 1/2, because up arrow is really 1/2, times 1/2 minus 1/2 plus 1 times L. And now it flips the up arrow to a down arrow. So this is just H bar. The square root turns out to be just 1. And this is L down arrow. Okay, and now we're finally ready to put this together with these two things. And we get that L plus 1/2, L minus 1/2 in the total angular momentum basis is equal to 1 over square root of 2L plus 1. The H bars cancel, and we get L down arrow plus square root of 2L, L minus 1 up arrow. Okay, so now we've constructed our second state out of 4L plus 2 total states that we need to construct in the end. Okay, and so now the strategy is just to keep acting with J minus until we can't get anything more out of it. So we act with J minus again. Okay, and so on the one hand, if we act on this state that we've just constructed with J minus, we get from the master formula, we get H bar times L plus 1/2 plus L minus 1/2 times L plus 1/2 minus L minus 1/2 plus 1. We're plugging in what L and M sub L and are. or J and M sub J are. This is acting on L plus 1/2, L minus 3/2, because we've lowered the unit of J by 1. Okay, and on the other hand, so if we solve again for the thing we want to know, which is this one, okay, that gives us that L plus 1/2, L minus 3/2 is 1 over 2 h bar square root of L, that's from that square root, times L minus plus S minus. Okay, times that state, which we already know in the product basis, it's this mass. Okay, and so we need to plug that in. That's going to give us 1 over 2 h bar square root of L times L minus plus S minus acting on 1 over the square root of 2L plus 1, L down arrow plus square root of 2L over 2L plus 1, L up arrow. Okay, now we have a bunch of things we have to do. We have to basically distribute this operator over these two states. So let's just do that. This is the same prefactor. And then we go back to our formula for how an angular momentum minus operator works. Okay, and so for the first term, we get h bar square root of L plus L, L minus L plus 1, L minus 1 down arrow. That's from L minus acting on this state. And from S minus acting on this state, we get nothing because S minus acting on a spin that's already down tries to lower it further, and it can't. So we get plus 0. Okay, and now we need to do the same sort of thing for this part. So that's plus square root 2L over 2L plus 1, h bar square root of L plus L minus 1, L minus L minus 1 minus 1. All of that acting on L minus 2, up arrow, plus, this should have been an L minus 1 here, sorry, plus h bar square root of 1/2 plus 1/2, 1/2 minus 1/2 plus 1 on L minus 1 down arrow. Okay, and so now when we simplify this, we notice that, aha, this term and that term are the same state. So we're going to need to add this coefficient to that coefficient after we simplify them. And so the result will only have two things in it, and it simplifies to 1 over the square root of 2L plus 1 times square root of 2 L minus 1 down arrow plus square root of 2L minus 1 L minus 2 up arrow. Okay, so we've constructed one more of these states. We've now constructed this state in the total angular momentum basis in terms of the product basis. And so we keep doing that in exactly the same way. And if you do it enough times, you realize there's a pattern. And so the general formula, which you can prove mathematically using induction, is the following, that if I take the state L plus 1/2 m in the total angular momentum basis, that's equal to 1 over the square root of 2L plus 1 times the quantity square root of L minus m plus 1/2, m plus 1/2 down arrow, plus square root of L plus m plus 1/2, m minus 1/2 up arrow. Okay, so a nice thing about this formula is you can sort of see how the z components of angular momentum work. On the left-hand side, we have total angular momentum in the z direction of m, and that can split into two parts. And the only two parts it can split into are m plus 1/2 and down arrow. Down arrow is minus 1/2, and m minus 1/2 and up arrow. There are no other combinations that can possibly work because all we have to work with is up arrow, down arrow, and up arrow. So it sort of had to be a linear combination of this form. And then what we've done is we've done the hard work of figuring out what the coefficients are that go in front of those two possible terms. But there couldn't have been anything else. Okay? All right, and so that formula is valid for the following possible values of m. So the possible values of m are from minus L plus 1/2 up to L plus 1/2. Okay, and the way that works is we started with this one. That was the largest possible value it could have, and then we kept acting, moving that direction. And when we get to m equals minus L plus 1/2, then when you plug that in, this term actually vanishes and goes away. And then this term turns into the lowest possible state that has this value of L plus 1/2. Okay, so we've now constructed a whole bunch of these states. How many have we constructed? We just count up the number of m's that we have here. That's the number of states. So the number of states that we've constructed is, we've already done this counting actually, is equal to 2L plus 2. Okay, now remember the total number of states here was 4L plus 2. So I'll write out of 4L plus 2. So we're missing 2L states that we have to construct next. And what are those 2L states? They are the states that we need. So we need L minus 1/2 m type states. Okay, and there will be 2L of those. So unfortunately, we can't construct those out of the states that we already have here, because anytime we act with a J minus, it's going to change m, but it's not going to change the total J quantum number. So we can never get an L minus 1/2 out of an L plus 1/2 state by acting with J minus. It just won't work. And so we need another trick. And so the trick that we're going to do is to write down the most general thing it could possibly be, and then solve for the coefficients. Okay, so what's the most general thing it could possibly be? For L minus 1/2 m. Okay, and the product basis, one thing it could be is it could have orbital quantum number m plus 1/2 and down arrow, because m plus 1/2 minus 1/2 gives m, so that works. And then the other thing it could possibly be, and I'm going to leave some space here for a coefficient, is m minus 1/2 up arrow. So I don't know what linear combination this is yet, so I'm just going to call these constants a and b. Okay, but there's nothing else it could possibly be. And so now we need to find these constants. Okay, so how are we going to find the constants? We're going to use a math fact that we proved a long time ago. And that is that we know this must be orthogonal to all the states we already have. Okay, and the reason is that both the state that we're trying to construct and all those other states, so really the one that matters though is the one that has the same m. That's why I'm saying both here. So both are eigenstates of a Hermitian operator. In this case, the Hermitian operator is j squared with different eigenvalues. So we have some theorem from a long time ago that says if you have a Hermitian operator with eigenstates or eigenkets that have different eigenvalues, they have to be orthogonal. Okay, so let's write down that fact in an equation. So I'm going to start here with the bra for the state that we've already constructed, which is, oops, proportional to, we don't need the denominator. We're just going to set this thing equal to 0 anyway. Okay, so this is this thing that I'm writing. I'm rewriting the bra corresponding to this state. But I'm neglecting that because I'm just going to set it equal to 0. Okay, and then there's a square root of L plus M plus 1/2, M minus 1/2, up arrow. Okay, and then here I'm going to write our candidate state. Oops. And then we're going to use orthonormality of the basis vectors, which says this inner product is 1, and so is this inner product. But all the other inner products are 0. For example, this one with that one, or give 0. Okay, oh, so this whole thing is supposed to equal 0 for orthogonality. And so when you work that out, that gives you A times square root of L minus M plus 1/2 has to equal minus B square root of L plus M plus 1/2. Okay, and so that's the information we got out of that. It turns out that no matter how you twist and turn and try other equations, you'll never get more information than that one equation. And so that's all we have to work with. And so we have one equation for 2 unknowns and we can't solve. So we have to just choose something. And so what we choose is we choose A to be real and positive. Now, not everybody makes that choice. Different books sometimes use different choices. This particular choice is called the Condon-Shortley choice, or the Condon-Shortley phase convention. So it's really a choice. You could choose A to have any crazy phase you wanted, any crazy complex phase you wanted. Nobody can stop you. But why would you do that if you don't have to? So we choose A to be real and positive. And so in terms of that, with this one equation, we can eliminate B and just write it this way. Our state L minus 1/2 M is equal to, I'm going to call the constant C for constant. Okay, and so we found that it's this linear combination. The other one has to have a minus sign though because of this minus sign. Okay, so unfortunately we can't get rid of all the minus signs. That would be too good to be true. Okay, so now we have our state. C is real and positive by our choice. And now we can fix out what C is by requiring the thing to be normalized. That won't affect the phase of C, but at least it will tell us the magnitude of C. So if we compute the normal of this state, we get C squared times L plus M plus 1/2 plus C squared L minus M plus 1/2. Notice these are orthogonal basis elements. So when we take the cross terms, they give nothing. So this whole thing is supposed to equal 1, which tells us C squared times 2L plus 1 is equal to 1, which tells us that C is equal to 1 over the square root of 2L plus 1. Notice we're assuming it's real and positive. And so finally, we figured out what the states L minus 1/2 M are. Namely 1 over square root of 2L plus 1. And then we just write what we already had figured out. Okay, so it's this linear combination. So down arrow minus okay, so once again, this is a linear combination of the only two things that you could possibly write down in the product basis that would give you the right total J sub Z. Okay, and this is valid for the following values of M, namely minus L minus 1/2 in parentheses up to L minus 1/2. Okay, and the number of those, if you count them up, is indeed the 2L states that we were talking about. Okay, so we have found, in fact, the full set of total angular momentum eigenstate basis states in terms of the product basis. So recap, we found the total, that means J squared J sub Z, orthobasis states okay, Jm as linear combinations of the product orthobasis, which means L sub Z and S sub Z in this case, states, which were M sub L and up arrow and M sub L and down arrow. Okay, any questions on that? All right, so let's, now that we've done that, we're ready to set up the most general case, which we will start on next time. So the most general case is just any angular momentum that we can form out of any other two angular momenta. And by the way, you can do this recursively. You can take two angular momenta, add them together to get a third, take that third angular momenta, add that to another one to get another one, and keep going until you've got the grand total of all total angular momenta. Okay, but the idea is J1, J2, J and M are the total angular momentum basis. This is a linear combination of J1, J2, M1 colon M2. Sometimes I put the colon in there to distinguish this set of four numbers from that set of four numbers. And if we want to know what the form of the linear combination is, we can use completeness. To write it as a sum over all M1s and M2s of J1, J2, M1, M2. So we're putting in a complete set of states here. I guess I should be consistent and put my colons in here. Okay, and so that writes down what we claim to accomplish. This is the linear combination, and these are the coefficients. And so those are called Clebsch-Gordan coefficients. Okay, and you can look these up in tables. Or there's even software that will compute them for you if you can't find a table with these values in them. But we have, in fact, done this for the case of the spin and orbital angular momentum basis. So all we have to do is compute the inner product here, and that's the Clebsch-Gordan coefficient. And then once you know the Clebsch-Gordan coefficient, for one example of a given J1 and J2, then you know it for any system, and so you can apply this to get what the linear combination is that gives you the total angular momentum basis. Okay, so just for example, we could compute, the one example that we've done is you can compute this Clebsch-Gordan coefficient for the case that J1 is L and J2 is 1/2. Okay, and so what we found, for example, is that L 1/2 L plus 1/2. I guess I'll write this as down arrow. I could write minus 1/2. L 1/2. Oops, this was wrong. This should have been L. Okay, and then L plus 1/2. Oops, I'm messing this up somehow. Okay, let me do this next time anyway, because there's something, I wanted to say some things about the final, and so I'm not going to get this right in time today without talking about the final. So let me erase this, and we'll do this next time. Okay, so the final is going to be handed out within seconds. It's going to be a take-home. There are rules associated with it that are on the final exam itself. Okay, you cannot work together. You are on your honor to not work together. You're also on your honor not to compute, not to use websites like Chegg. So no external help, except for generic math sites like integrals.com and Wolfram and things like that. If it's something that's just generically computing an integral, then you can use a website like that. So except generic math software. Okay, it's open notes, and that means all materials for this class. But not for other classes, and so you're not supposed to use outside quantum mechanics books, just the notes for this class. Okay, but math books are okay. So if you can't remember how to do some integral and you think you need to know how to do that integral, you can go ahead and look that up in a math book. Okay, and then finally, it's going to be due on Friday, December 11th at 7 p.m. Okay, so all of that information is listed on the exam itself. Please read it before you read the rules before you start working on it. It's got 7 problems. So make sure that when you look at your PDF file, you see all 7 problems. So how you manage your time between now and the end of finals week is up to you, but I would sort of recommend at least looking at it before finals week starts. Because 7 problems, the problems are probably a little easier than what we've had for homework as far as length, but they might be conceptually a little trickier in some spots. And in part, that's because we haven't had homework sets that cover everything that's on the final. It's sort of a hybrid of a final exam and a homework set. Okay, and then the last thing about it is because it's supposed to be a replacement for your final exam, I won't be giving out hints in the same way that I would give out for a homework set. So if you have interpretation issues as to what does this problem mean, then I might answer those. I probably will answer those if I feel like I've really been ambiguous. Or if you want to know interpretation of these rules, again, I'll answer questions about that, but I won't be giving hints the same way I would on a homework set. All right, are there any questions on the lecture or on the meaning of the final exam? All right, well, if not, then I will be emailing those out to you shortly, so make sure you get it. If you haven't gotten it within a few minutes, then something went wrong and you should send me an email asking for your final exam. And I will see you all on Wednesday.
Thank you, Dr. Martin.
Thank you.
All right,
Thank you.
good luck.
Thanks.
Thank you. Professor,
Yep.
how are you? I had a question. I don't know if you, I submitted the last homework last week. There was something that just kept confusing me, so I used an alternative method on that first problem. I don't know. I haven't checked my email yet. I don't know if you've. I don't know if you've solved them. I don't know if you've graded them or not.
I have not graded them. I'm probably going to grade them today.
Yeah, I don't know if you responded to my email or either. I haven't checked yet. But the thing is that there was this method I kept trying to use and it didn't work.
Okay.
I don't know. Did you see my email last week?
Possibly.
I'll wait until you, huh?
Possibly.
I can wait until you grade them. I think if you see my paper, you'll see what I was trying to do.
Okay. Yeah. Well, let's see. I got a lot of emails from you here, but so it might be. Yeah, it might be the most efficient thing is I'll also be sending the solutions, and so maybe between the two of those, you can figure out where things might have gone wrong.
Okay.
I haven't even started grading them yet. I was going to do that today. So.
Oh, okay. Okay. I just wanted to know what I was doing wrong in that one. Yeah, that was something I saw from my previous quantum course. I was trying to use that, but it wouldn't work. I don't know. So that's why I was trying to figure out what I did wrong.
Okay.
Okay.
Yeah, let me grade them. I'll have them graded probably by the end of today, hopefully.
Yeah. And I think I like enclosed, I took a picture of what I was trying to like, what the source I was using from last semester, the example that she had given us. So I enclosed that in an email. I don't know if you saw, and I just wanted to know why I couldn't use that for this one. So, I don't know. Whenever you get a chance.
Okay.
Thank you so much. Thank you for the semester. Huh?
I'm sorry, go ahead.
I said thank you for the semester. Thank you.
Oh, no problem. All right, yeah, so let me know after I grade it, let me know if if you still have questions.
Okay, thank you so much.
All right, have a
Have a
good day.
nice. Bye.
Bye.